Okay, so today we are going to look at section 7.2, the natural, logarithmic, and exponential functions. All right, so what you see in front of you is the power rule for integrals. All right, so we learned in the first semester calculus that whenever we're dealing with a power function, now the discussion in first semester calculus was around exponents that were rational numbers. Right? There was no talk of, or most likely you didn't talk about irrational exponents and what that actually represents. But for the most part, for any rational number, this power rule for integrals holds, except for one particular value, right? That value being, right, we can never divide by 0. So this holds for everything except this value here. So there's essentially kind of a hole missing here in our rule, right, for the power rule for rational numbers. So whenever there's kind of this, I guess, outlier here, or kind of a rule doesn't follow, here we think, okay, well, what is special about this function, right? So what we're gonna take a dive here is a look at this function here. Okay, and in particular, we're going to define a function, f of x, that is different than any function, or different than the types of functions we're used to seeing, right? We're used to seeing like polynomials or even trig functions. But this function that we're going to define here is in terms of an integral. So we're going to define the definite integral here. All right, again, remember t is just a dummy variable. The independent variable here is the variable x. All right, and we're going to define this, then essentially the domain of this function would be for values of x that are bigger than 0. Okay, not equal to 0, because then we'll see it is in fact undefined there. Right? And the reason for the choice of this domain is that restricting or defining a function in this way leads to some very interesting results. Okay, now the fundamental theorem of calculus states that at least, right, this is a continuous function on the interval, right, x greater than 0. States that we at least have a theoretical solution to this, that we can take the derivative of this. I know that derivative of this function f of x, right, says the derivative with respect to x, 1 x dt over t, is 1 over x, right? Again, that's just an application of the fundamental theorem of calculus. So I know that theoretically I can take the derivative of this function that I've defined in this way. All right? And again, right, we say, so f of x is the antiderivative, right? Capital F of x is the antiderivative of f of x equals to 1 over x. Okay, now here we might say, all right, well, that choice of 1 really could be any number, right? It could be just some constant a, right? As long as it's in the interval 0 to infinity, and that would still yield the same result, right? So why is it at 1? Why do we choose to define it at 1? Right? And the reason for that, right, that this particular function has the following properties. Right. The first one being is that f of a times b can be and it can be shown, and we will in fact prove this, is equal to f of a plus f of b. And f of a over b is equal to f of a minus f of b. All right, so essentially what's happening here, it changes a multiplication into an addition and a division into a subtraction, right? In other words, theoretically simpler operations, right? From multiplication to addition and from division to subtraction, right? And then now we could start thinking, okay, I've seen functions that exhibit this behavior before, right? Those were those logarithmic functions. All right. Now, in a typical calculus course, or excuse me, pre-calculus course, we're usually taught the exponential and then a logarithm from there. Here we're taking a different approach, right? We have a this function f of x. Right, which we are now going to define, right? So when we are working with this function capital F of x, we won't use the integral definition. We're gonna just kind of rebrand it essentially, right? So in fact, what f of x is gonna be, or what we're gonna define f of x to be, is what is called the natural logarithm. Right, so it arises naturally, right? So this ln of x is equivalent to the integral dt over t. All right, so when we think kind of, maybe you've asked yourself before, what exactly is a logarithm? Well, in fact, there is really one logarithm, right? This being the natural logarithm. Any other logarithm that you work with is simply a ratio of the natural logarithm. And we'll kind of see why that's the case as we move along in this section. Now again, for this function here, right, this is defined for x greater than 0. All right, so that is the domain. All right, so at this point, we just define it. Notice that there is no talk of a base, right? You may have an idea already or know or what the base is for this logarithm, and we'll actually kind of discover what that base is along the way here, right? But for now, we simply state this as the definition for the natural logarithm. All right, notice there's no talk of a base or even the relationship that it has excuse me, with the exponential, right? And we already kind of, at least, you know, in pre-calculus class have been kind of taught the relationship between the both of them here, but here we're just simply defining the natural logarithm as this integral function. All right, and then this idea of a base will come a little later. All right, now we already know this new function is what is called a transcendental function. Right, so it doesn't follow, as we'll see, the same kind of properties like algebraic functions. It's not a function constructed from addition, multiplication, division, subtraction, right? Those types of operations. Completely different type of function. Right, now we already have seen, right? We already know what the derivative of this is. Right, so we've seen from the fundamental theorem of calculus, the derivative of such a function is 1 over x. Right, and again, the chain rule will still apply here. Right, where u is some function of x, we'll have 1 over u times du dx. Right. So now we can add these to our common derivatives, right? So for example, here, let's do some examples here. let's say we had the derivative, excuse me, with respect to x of ln of 3x. Again, applying the chain rule. This is an application of this one right here, right, where u is 3x. So chain rule says take 1 over 3x, right? Again, ln of whatever, the derivative will always be 1 over whatever that function is, right? Times the derivative of the argument 3x, which is 3, and then that just reduces to 1 over x. All right, and let's try another one here where, excuse me, we use the chain rule as well. Here we'll have, again, 1 over sine of x, derivative of sine, cosine x, and we get cosine x over sine x, otherwise known as the cotangent of x. Okay, so let's see here. Moving along. All right, now one thing to notice from our first example is that if the function inside the natural logarithm here is a constant times x, in other words, that there was nothing special about that 3x, if it took the form of this, where a is any real number, then we would always get back 1 over x. Actually, let me clarify that. Not any real number, any positive constant. Any positive real number. Right, if we assume that x is a real number bigger than 0. Right, then a would also have to be a positive constant. All right, now this fact actually is going to lead us directly to some of these laws of logarithms that we are familiar with. Right, so for example, let's introduce here our first kind of theorem of these logarithms or laws of logarithms that we've probably seen before, but now we're going to take a different approach to actually proving them and showing that they are in fact true. Okay, so if a and b are positive, then the natural log of AB is equal to the natural log of A plus the natural log of B. Okay. All right, so let's actually prove this here. All right, now for our proof, we want to use the fact that the natural log of ax and the natural log of x have the same derivative. Right, and again here for x is a positive value, right, from 0 to infinity. And a is also some positive real number. Okay, so the reason that, well, one thing that I want to recall here, kind of refresh your memory, is that if two functions have the same derivative, then a theorem from first semester calculus tells me that their difference between the two functions must be a constant, right? In other words, the fact that these have the same derivative implies that the difference of both of them, in other words, this, must be equal to C. And again, keep in mind, we're dealing with positive values for x. Okay. So now let's try to see if I can find what that constant C must be. Okay. So the way I'm going to do that, so the next step here, I want to find C. All right, and the way I'm going to do that is I'm going to let x be equal to 1. All right, so that means that here C is equal to the natural log of A minus the natural log of 1. All right, if I let x is equal to 1. But remember or recall the definition of the logarithmic function. If x is equal to 1, what is the integral when the upper bound and the lower bound are the same? The value of the integral is 0. So what we have here is, right, another property of our logarithms, right, again derived from calculus and not just from our kind of definitions in a pre-algebra course. The natural log of 1 is equal to 0, so that leads me to the conclusion that the natural log of A is the constant C, right? In other words, putting this together, we have the natural log of AX minus the natural log of x is equal to the natural log of A. Right? Now another way of rewriting this is that of A. And now you can see here by x is a variable here, but let's let x equal to B. And again, that is any positive constant. And we arrive at the conclusion that we were trying to prove. ln of A times B, where A and B are any positive constant, is equal to the natural log of B plus the natural log of A. Right? And that is the proof of our first logarithm property. Right? And again, one thing to notice here, there was no, the proof was through properties of the integral, so it had nothing to do with exponents, which I think was probably how, in at least a pre-calculus course, the way they were kind of treated. But here was strictly through the derivative, the integral and properties of the integral, and properties of the derivative as well, of ln of ax and ln of x. Okay. All right, so that proves that first property of addition. Let's look at the second one, our second property for logarithms. So for this one, we'll say if A and B are positive, the natural log of A over B is equal to the natural log of A, natural log of A minus the natural log of B. Okay. All right, so let's actually do this proof as well. Now I'm gonna, in this case, I'm gonna use the fact that I've already proven above, right? This one here. I've proven this, so I can now, I don't need to reprove it every time I use it. So this is now a fact, right? It's theorem, I proved it, so now I can use it as a fact. So what I'm gonna do here is we're gonna say, okay, let's say I'm going to start with the natural log of a, right? A is some positive constant. All right, and I'm going to rewrite this as the natural log of b times a over b. All right, and again, b over b is 1, so this is equivalent. All right, and again, remember b is some positive constant. Okay, so what I'll do here is the previous theorem told me that I can split a multiplication into addition. So this can be rewritten as natural log of b plus natural log of a over b. Right, and then the left-hand side remains the same here. All right, and again, this was the reason for this was our previous theorem. Okay. All right, and now let's do some algebra here, and let me bring the ln of b over to the other side. So we have the natural log of a minus the natural log of b is equal to ln of a over b. And that concludes the proof here, right? So here is our second rule for logarithms. All right. All right, so those are two of some of the basic properties of logarithms. Notice here that it is applied to the natural logarithm. Still no talk of a base. We'll talk about that shortly here. Now let me here. Our next property I'll state without proof here, so I won't prove this one, but now maybe we can at least just state another one of the basic properties of logarithms. If r is rational, then the natural log of x to the r is equal to r ln of x. Okay. All right, and again, I'll state this one without proof, and we'll just kind of use it as fact here, just for kind of the sake of time here. Excuse me. All right. So let's all right, so now we have some basic properties of the natural logarithm. And now let's take a look at what would the graph of a natural logarithm look like, right? So if we look at this here, so the graph of ln of x. All right. So f of x is equal to, again, the integral definition. Of x. Okay, and let's draw a graph of this here. So let's say that this is 1, and our graph would look something like this. this will be 1. Okay. So the graph of our function looks like this. All right, now I highlight 1 because that's where we chose our integral to be defined at. Now x is just, remember x is some value bigger than 0. So just I'll choose arbitrarily 1. Let's say that x is here, but it could be to the left of 1 as well, right? So when x is just some value there, we can interpret as the area definition of the integral. We could say, all right, this integral is representing the area under the curve. All right, now a couple of things, and again, deriving this from the integral, I can state that ln of x is undefined for x less than or equal to 0. All right, the integral doesn't exist if the domain of integration includes the origin. All right. Okay. Another thing is that notice here the area is positive here, so ln of x is positive when x is greater than 1. All right. 0 is equal to 0 when x is 1. Right, that would be the integral over 1 point, which we know from our first semester calculus is the value of that is 0. Now, I also know that it will be negative. In other words, ln of x is negative less than 0 when x is between 0 and 1. Okay, and the reason for that, again, that comes from the integral definition. When if we interpret that the smaller value is on the upper limit, when we switch them around, we introduce a negative sign. Okay, so all of this, remember, keep in mind that this here is not the graph of ln of x, right? This is the graph of 1 over t. All right, where this is our t-axis, y, right? ln of x is the area here, right? This is the area under the curve. All right. Okay. So let's see if we can figure out, with all of these properties that we have here, let's see if we can kind of put together a graph. All right, so here is, let's use some of our calculus techniques here to determine the shape of the graph. Okay, so I know it's negative between 0 and 1. I know it's positive after 1, and it's 0. So far, let me try not to scroll too fast here, but let's see so far what we have here. All right, so far I know 1 point on this graph. And that is when x is 1, the value of the function is 0. So I know that is the x-intercept. I know that to the, excuse me. All right, I know that to the left of 1, but before 0, that it is negative, right? So it goes down below the x-axis. And to the right of 1, it is positive, so above the x-axis. Now, if I take the derivative of f prime of x, or the natural log, remember that's equal to the natural log, and again, always keep in mind the domain is positive real numbers. All right. So f prime of x is equal to 1 over x. Since x is positive, this is always positive. And in terms of what that means from the graph, it is an increasing function, which means that f of x is always increasing. Remember, positive derivative means increasing. Now, what you notice, you may think, you might start looking at this function here, right? But the limit as x gets bigger and bigger towards infinity is going to 0, and that is correct, right? It is going to 0, but it is not 0, right? It's still some positive value. So it's increasing, but not very quickly, right? The rate of increase is very low, right? But still increasing. All right, now if I take the, so now I know I have start thinking of a shape of what this graph is taking on. If I look at the second derivative of 1 over, or the derivative of 1 over x, we get negative 1 over x squared. Now the second derivative is always negative. So that means that it is concave down. All right, now putting this together, we could see, all right, that means that always increasing, so that means it's coming from negative infinity, concave down, so it looks something like this. All right, and that is the graph of the natural log of x. Right, it satisfies all of these properties. All right, undefined when it's less than 0. We see there is no graph to the left of the y-axis. Always increasing, always concave down. Now, another thing to, and here we can state here, so f of x, ln of x, the domain is from 0 to infinity. Now the range, and I'll state this without proof, and we can kind of, the proof would be we can visually see this. If it's always increasing, all right, that means that it should take on all values of y. So the range, all right, always increasing means it's coming up from negative infinity, or as you approach 0, the values are getting more and more negative. And as you go to infinity, the values are increasing, right, at a low rate, but still increasing, right, which means that the range is going to be from negative infinity to positive infinity. Okay. Now, another thing that we can notice here from the graph now is that ln of x is a one-to-one function. Right, and just kind of thinking of that, like, why must that be true? Well, if it's always increasing, that means that the values that each value that it's taking on is greater than the previous value. So there's no values that they're all unique for any value of x. In other words, it passes the horizontal and the vertical line test. Mm-hmm. So if it's a one-to-one function, that means that there exists an inverse. Okay. All right. Okay, so let's take a look at trying to find the inverse, right? So now finding the inverse of the natural log of x. Okay. All right. So let's start by defining this function. All right. Now I use this kind of funky notation here. Moving forward, we won't use this. We kind of go into it and say, all right, I don't know what the inverse is, so then we just define it as natural log inverse of this natural log. Okay. Now this is differentiable because it's the inverse of the natural log, right? So in other words, here, let's take a look at if this is the inverse. Then what must be true is that the natural log of y must be equal to x, right? And again, these are just properties of inverse functions. Okay. So let's start by taking the, so now let's use here implicit differentiation. And I'm going to take the derivative here. Oops. I'm going to take the derivative of this function here. I guess here, let me be a little less sloppy. Okay, remember it's a function of x, right? Y is a function of x, so we use our implicit differentiation here, where we say, all right, 1 over y times dy dx. Right? And the derivative of x, that's our independent variable, is just 1. Right? And here, solving for dy dx, we see the derivative, we get that y. In other words, dy dx is equal to the inverse of the natural log. So it has the same derivative. Okay. Now, at this point, let's introduce some new notation here. Right? The natural exponential function. Okay, so the natural exponential function, so the inverse of the natural log is called exp, the exponential, and it is defined by the following statement. If y is equal to the exponential of x, that means that if and only if x is equal to the natural log of y. Okay. Now, again, one thing that kind of want you to kind of realize here, the exp notation, and later we're going to call this, we'll figure out what the base of this is, right, which we still have, right, and this natural log, these are all just notations made by by mathematicians throughout the years that this is what we call this type of function, right, and again, this is all derived by that integral of 1 to the x of dt over t. Now, we already know a lot of things about this natural exponential function, right? And that all this comes from our our properties of inverse functions, right? So the domain, right, is going to be the range of the exponential, which is negative infinity to infinity. The range, which is the domain of the natural log, which would be 0 to infinity. All right, so the domain is the range of the natural log, and the range is the domain of the natural log. Okay, so if we take a look at some graphs here, we could see again another thing that we know about about inverses is that they are reflections across that line y is equal to x, right? And that's what we're seeing right here. Okay. All right. And then again, also through properties of inverses, we can derive some properties the natural exponential. All right, so one of the properties is the composition leads us to the value of x. Now again, as long as x is in the domain of the natural log, so this will be true for all values of x greater than 0. And if we go vice versa, the natural log of the exponential of x will be equal to x, and this holds for x to be any real number. Right, the r, that fancy r there is, represents any real number. All right, because again, looking at the graphs here, right, any value of x, even the negative ones, yield a positive result. So not 0, a positive result. Okay, so that will hold here as well. Okay, now a little more about this exponential. So I'll introduce two of these properties here. And again, I'll state these without proof here. But we can prove them using the, actually let me prove one so we could see how, again, without use of exponentials or exponents here, that we can prove them using properties of logarithms. So let's look at the first one. Let me say for all real numbers u and v, the exponential of u plus v is equal to the exponential of u times the exponential of v. Okay, so let's look at what the proof of this looks like. Okay, so we'll start with exponential of u plus v. And again, using properties of the inverses between the natural exponential and the natural logarithm, I can rewrite u and v in this form. Okay, and again, this is just properties of inverse properties, and I know I've defined that the natural exponential is the inverse of the natural logarithm. Okay, so the next step here, using properties of logarithms, the logarithm's addition changes it to a multiplication. U times exponential of v. Okay, and again, looking at this here, we again now use the properties of the exponents. Exponent of a logarithm, they essentially counteract each other. So this result here turns out to be the exponential of u times the exponential of v. All right, and that holds, that proves our theorem. Okay. Excuse me. All right, now our second theorem here for this properties of exponentials. Now I'll state this without proof and we can just use the results in our work here. If R is rational, then all right. Okay, so it changes when we raise it to R, it takes the exponential and it changes it into a multiplication. All right. Okay, so, and again, I'll state this one without proof. So let's kind of summarize. What we have so far. Okay, so far we have seen here, and even from the graph, we could see that the EXP established that it behaves like an exponential. All right, but again, what is the base? Right? What is the base of this exponential function? All right, is it 2? Is it 3? Is it some other function? And as it turns out, that the base of this, using a limit, which again we'll do in a later section here to actually determine the value here, using a limit, we come to the conclusion that the base of the exponential is this number e, right? So it's a constant e, count 2, 7, 1, 8, 2, 8, etc. Right? So this is an irrational constant. Right? In other words, that the exponential of x is the same as our exponential function e to the x, right? And in fact, we'll be using this notation throughout, for the rest of our work here. Instead of the exp, we'll use that e to the x. Now, what does that mean? That means that the natural log of e is equal to 1 to the e over t, which is going to be equal to 1. Okay. All right. Okay, so to kind of wrap this up for right now, we could say, all right, exp so far we thought of exponents to be rational, but actually we do not need to be confined to that, right? So for example, what do I mean by that is we could say, all right, if y is equal to e square root of 2, all right, that means that the natural log of y is equal to the square root of 2. Okay. Or in other words, another way to think of a rational exponent, because we know what, or excuse me, irrational exponents, because we know how to treat rational exponents, right? We think of if we have a fraction of an exponent, the numerator is the power, and then the denominator is some kind of root, right? If it's 2, it's the square root. If it's 4, it's the fourth root, right? But what do we do with root 2? So a way to think of this is that when we have an irrational exponent, and think of it in terms of a logarithm, e to the root 2 is the number whose logarithm is square root of 2. Okay. All right, and that's how you want to interpret irrational exponents, right? In terms of logarithms. Okay, so to kind of summarize here, so what have we learned here? Y equals to e to the x. It means that x is equal to natural log of y. All right, and we have e to the u plus v is equal to e to the u times e to the v, right? Those are the exponential, the one that we proved. And then it can also be shown, again, we didn't do this, but we can show that e, right? And then the other property here, e to the x r, e to the r times x. Right, and again, the composition properties, this is true for x greater than 0, and then ln of e to the x is x for all real number x. All right, so thank you.